It's pretty mind-blowing when you think about it. Enrico Fermi winning the Nobel Prize for artificial radioactivity way back in 1938. Talk about being at the forefront of science. It's like we're getting a glimpse into the birth of nuclear physics right from the source Fermi's Nobel Lecture.
Absolutely. And you can really see how he's building on what others like Ernest Rutherford were doing. Remember, Rutherford was already experimenting with bombarding atoms.
Right. Using those alpha particles like tiny little atomic bullets. What gets me is how the choice of particle makes such a huge difference.
It all comes down to charge. See, Rutherford was working with alpha particles, and they have a positive charge. And guess what? The nucleus of an atom, it's also got a positive charge.
So it's like trying to stick two magnets together with the same poles repelling each other.
Exactly. It's called the electrostatic barrier. But now, along come neutrons discovered just a few years before Fermi's lecture. Neutrons have no charge. They're the key to getting past the atom's defenses.
And this is where Fermi's brilliance shines through. He finds a way to produce these neutrons, but not with some massive, complicated contraption.
It's almost elegant how simple it is. He used this glass bulb filled with beryllium powder and radon gas.
Radon gas, like the stuff they worry about in basements.
Well, kind of. But in this case, it's actually useful. See, radon naturally decays and releases alpha particles. Those particles then hit the beryllium and bam, neutrons.
Wow. Just goes to show what you can do with some sharp observation, a little ingenuity, and a whole lot of scientific curiosity. But having a source of neutrons, that was just the first step, right? What did Fermi do with them? So he's got these neutrons, right? What did he do? Just start bombarding everything he could get his hands on?
Well, yeah, pretty much. Fermi and his team, they went through the elements one by one, just bombarding them with these neutrons and really looking at what happened. And that's how they discovered these three main types of reactions that can occur when a neutron hits an atom's nucleus.
Okay, hold on. Break it down for me. What's actually going on inside the atom?
So picture this. You've got the atom's nucleus, right? Think of it like a fortress, and the protons are the guards. Now along comes this neutron. It's like a sneaky spy slipping past the guards because it doesn't have a charge.
Okay, I like this analogy. I like where you're going with this. So the neutron spy is in. What happens next?
This is where it gets wild. Fermi and his team, they found that there were a few possibilities. Sometimes the neutron goes into the nucleus, makes it all unstable, and then boom, the nucleus kicks out a proton, almost like a trade-off.
Wait, so the atom, it actually changes into a different element?
Exactly, because it's the number of protons that determines what the element is, right?
Right.
It's alchemy, but like subatomic alchemy.
Wow.
But that's just one way it can go down. Another thing that can happen is the neutron goes in, gets absorbed, but instead of kicking out a proton in the nucleus, it's like it releases this burst of energy like a gamma ray.
Now, for those of us who aren't nuclear physicists, what exactly is a gamma ray?
Right, so it's a super high energy photon, incredibly intense electromagnetic radiation.
Like the nucleus is letting off some steam after being bombarded.
Exactly. And when this energy release happens, it often creates what's called an isotope of the original element.
Yes.
Still the same element, same number of protons, but now it's got a different number of neutrons, so its mass is a little different.
Got it. Two types of reactions down. What about the third?
This one's maybe the simplest. Neutron goes in, hangs out in the nucleus, and that's it. But by joining the party, it makes the nucleus heavier. So you often end up with this bigger, often unstable isotope of what you started with. Fermi talks about this with aluminum. They bombarded aluminum-27 with neutrons and ended up creating aluminum-28, a heavier radioactive version.
It's incredible. Just one element bombarded with neutrons can lead to all these different outcomes. It must have been so exciting for Fermi and his team figuring all of this out.
Totally. They were basically rewriting the textbooks in real time. And get this, they didn't stop there. They thought, hey, what happens if we try this with even heavier elements like uranium?
And that's when things get really interesting, right? Because with uranium, they weren't expecting what they found. So they're hitting this uranium with neutrons, thinking they'll see more of these transformations, maybe even heavier isotopes, right? What did they find?
Well, the radioactivity they saw coming from the uranium after they bombarded it, it didn't line up with anything they knew. It was a real puzzle.
Fermi even says in his lecture, they're seeing something totally new here. He starts to think maybe, just maybe, he's created elements heavier than uranium, elements that just don't exist naturally.
Which is where those names come in oscenium and hesperium.
Yeah.
Elements 93 and 94. You can see why they thought that's what they were seeing.
Right, pushing the boundaries of the periodic table. But then there's this footnote in Fermi's lecture. And you know how it is. Sometimes the best stuff is hidden in the footnotes.
And this footnote, it's a game changer. because it mentions that Hahn and Meitner, other scientists, they had detected something unexpected in this irradiated uranium, barium.
Okay, so why is barium such a big deal?
Well, where's barium on the periodic table compared to uranium? It's
Right.
way lighter, right? And that suggests maybe instead of the uranium just getting heavier from absorbing neutrons, it was actually splitting apart, fragmenting into smaller pieces.
Hold on. So instead of building up these heavier elements, Fermi, he might have been splitting the atom.
Ding, ding, ding. That footnote, almost like a throwaway line, hints at the incredible discovery of nuclear fission. It really shows you how science works, this constant back and forth, always revising and refining what we thought we knew.
Even Nobel Prize winners, they have to be ready to see their ideas challenged, right? It really drives home how much we're still learning and discovering when it comes to science.
Absolutely. And this is where the story gets even more mind-blowing. Remember how we were talking about the power of neutrons to transform atoms? Well, Fermi found that if you could slow those neutrons down even more, it made them even better at setting off certain reactions.
Really? That seems counterintuitive. Wouldn't a faster neutron have more energy to interact with the nucleus?
You'd think so. But for some elements, these slower, what they call thermal neutrons, they're actually more likely to be captured by the nucleus and cause reaction. Fermi, he even designed some ingenious experiments to prove it. One involved a rotating wheel covered in paraffin.
So it's like slowing down gave the neutron more time to interact, kind of like in baseball, it's easier to hit a slow curveball than a fastball.
That's a fantastic analogy. And here's the kicker. Not all elements responded to these slow neutrons the same way. Some, like cadmium, they were incredibly good at absorbing them.
Huh. Why would that be? It's like they had a particular taste for those slow neutrons.
And that question, it opened up a whole new level of understanding about the nucleus itself. See, it's not just some random collection of particles in there. It's got energy levels, just like the electrons that are orbiting around it. And sometimes the energy of a slow neutron just happens to line up perfectly with an empty energy level in the nucleus, and bam, much more likely to be absorbed.
Wow, so you're telling me the nucleus is a lot more organized than it seems.
That's exactly it. And this whole understanding of how neutrons interact with the nucleus, all thanks to Fermi's work, it opened up incredible possibilities for scientific advancements, for technology, everything.
Amazing to think this all goes back to Fermi and his team just bombarding stuff with neutrons and seeing what happened.
It really speaks to the power of curiosity-driven research. Fermi's work laid the groundwork for so much of what we understand about nuclear physics today. And who knows what other secrets the nucleus holds, just waiting to be discovered.